Thank you very much, Michael, and thank you for the opportunity to speak in this event. What I would like to share with you today is a bit of the journey we had in our department over the past few years, trying to reap some of the opportunities in digitalization in relations to the research and educational activities we are running in our pilot plants. So basically, I will just present a little bit about our department to give you a bit of context. Maybe some of you might not have had the opportunity to visit us, but please drop by any case you feel. I will talk a little bit about our power plant and how we use it, both in education and research, and then sort of the overall strategy we have for digitalization as an engineering department. And then I'll go into two specific projects we have been developed. One we call the SCADA project, which is very much about data interconnectivity to different systems. And one is a virtual reality project, which is about training of engineering students. And what I will discuss here is primarily the infrastructure investments we have done, some use cases, and the lesson learned from all of this. But here's a photo of our department. You can see the two big yellow buildings, which is primarily office and general wet lab chemistry labs. We have the black building in the back, which is administration, some lecturing facilities, large room that we can gather the entire department, some modern pilot scale labs for biomanufacturing, also GMO certified. And the building in the middle, which also takes a fair bit of space, is our regular pilot plant. We have a section which is primarily setups used for teaching. We cover a wide range of all the classic unit operations at pilot scale there. And we have a more dedicated research lab for high temperature processes, catalysis, that kind of systems. So this is very much at heart to how we work in the department. As a department, we have approximately 340 students, both undergraduate and graduate levels. We have 190 PhD students currently distributed over 32 faculty members. So a mid-size engineering department in a European sense. Our pilot plant is constructed as a cross-departmental facility designed both to large-scale experiments, both for teaching and development processes. We can basically do all kind of transformation of matter in here. We use it also as a space to collaborate with companies. They could be companies coming and wanting to try to prove a concept at scale. It could be companies developing sensor technologies that need to verify again in scale, and in such we can function as a neutral ground also for collaboration between companies where it's difficult to share very specific data from their own production sites. This is just some pictures from our general process hall, which we use for the teaching equipment. Here is a picture from our newer pilot plant related to biomanufacturing processes, where we mainly have upstream fermentation from 5 up to 200 liters, and we have a number of separation unit, chromatography, filtrations, and so forth. We also have a GMO scaled pilot plant where we have 300-liter fermenter. We have centrifugation and other kind of solid liquid handling in there. And we have this large-scale pilot facility for high temperature processes and research related to that. So this just gives them a little bit impression about the type of facilities we have here in-house. We run a number of courses where we use these facilities. Most of them are experimental unit operation, primarily at the bachelor levels, but we also have a number of theoretical courses like process control or GMP, where we use pilot scale experiments as an integrated part of theoretical courses. We run a summer school in July for 80 to 100 US students coming and using our facilities for course in experimental unit operation. This is by far our most busy period. We are executing 200 to 300 exercise experiments over 3 weeks in that period. So it gets busy. So that was a little bit of context about how the department looks and what is our facility when it comes to steel. We have, as many others, had a process looking into what is our role in relation to digitalization and how could we support the chemical and biochemical industry as a research department in this area. And well, everybody is aligned when it comes to that digitalization is a priority. It might also be easy to agree on a lot of key topics relevant within this area and what is defined by what you can call Industry 4.0. It is a little bit more hard to say where do you actually make an input and impact and what is the role. So basically, what should we do as a faculty community in order to drive this? That has been a process for us, and we have worked very systematically in trying to define what is our role in here and define a strategy for digitalization. And basically, we have come up with this like one slider saying that we want to be at the forefront in the field of digitalization and research, innovation, and education within product design, process design, production, in chemistry, biotechnology, food, pharma, and energy. And that means that we want to be the people who can connect the domain knowledge within chemical and biochemical engineering with industry and the opportunities in digitalization. And we would like to be able to develop and showcase practical solution of digitalization that brings value. And in that sense, our pilot plant is a very important infrastructure because this is a playing ground and a test field where new technology can come into play with unit operations of reasonable size to prove concept and where we can actually work with advancing this field. So this is what digitalization means for us and where we believe that we should be able to make a contribution. So let me, based on that, go into the specific projects we have been launching. And the first one we call the Pilot 4.0 SCADA project. Well, the beginning is that we want to connect the physical entity with the digital entity, and we want to do that in a more systematic fashion that we were used to. If we go a few years back to 2021, we had a number of equipment and they were all connected to standalone PCs. And that gave a lot of issues in relation to actually having data stored at many different places and at different formats. And it was difficult to utilize all the data collections we do when this equipment is running. And there was a lot of context missing from that. So it just meant that we got low value out of all the measurements we actually collect from these systems. Also, the problem with having a direct PLC communication to a standalone PC is that you have to update the operating systems and the security protocols on every single machine, and it becomes quite heavy for us simply to do this and update all the machines. It also meant that many different equipment have different type of interfaces, and it was difficult to maintain and also to know the different systems. So it was not only to getting into a specific part of equipment, you also needed to learn how is that interface actually relating and communication. So there was definitely things that could be improved based on that. So this was not an Industry 4.0 ready facility we were having. We were quite clear on that. So this is a picture from our pilot plant. You can see here there's a bubble column distillation system, and there is the old PC standing next to it. So that was basically how our labs looked. It meant a lot of wiring. It meant old PCs. It was dissatisfying from the students' point of view. They were expecting something a bit more modern. But with onset on that, our ideas also taking onset in this digitalization strategy, that was to develop a system like here. So you have data generating entities. So that could be all the sensor and actuators on plant. It can be what comes from the PLC, but it could also be a simulation model in itself. And all of this could communicate with a digital twin layer through the communication protocols, for instance, OPC UA, such that you within the digital twin framework can run both your data processing, your process models, your control algorithms for the type of services you're interested, and all of this output can then be accessed either through a web interface, it can go to data storage, it can come to consoles for development and so on. So we wanted to have a framework that was more taking all the different kind of equipment into one umbrella that enabled a system like that. So that was sort of our starting point on the drawing board. So what did we do? We were very lucky, first of all, to have a grant from the Novo Nordisk Foundation that allows us to invest in new servers. So we bought expensive servers for both the Windows servers to run industrial standard SCADA system based on Siemens WinCC. We bought a server to install a Kubernetes cluster. We invested in this vNode server, which is an IoT enabler in this system. That means now all the equipment is communicating wireless through Cloud Connect with these servers, which is physically located at least 30 kilometers away from our campus at another campus in Denmark. So we now got this cloud infrastructure to both operating our process, but also our data storage. We have invested in building up a relational database within this Kubernetes clusters. We have developed new HDMI for operating the equipment, which is now a web-based interface, so that the students operating process equipment, they are handed out a tablet, and it's simply running this SCADA system in the tablet. So this is sort of the core infrastructure in our new plants. So what does that enable? Well, basically we have this online PLC communication that allows this cloud infrastructure. We have the web-based SCADA interface. So basically we are having the SCADA system in a cloud solution. We are communicating with vNode, which is the IoT gateway that enables both that we can capture all the live data from the SCADA system, but we can also capture the metadata, as we heard, which is so important for the contextualization of data. And we can store that in a central cloud server in the Kubernetes system. So this is sort of how the end results in this looks like. We use vNode as the main gate for how the facility can communicate through the server, through the firewall, based on certified data access. So basically we get the tag IDs. It can communicate either as a web protocol, OPC protocol, MQTT, and that means through the IP address, we simply get the port readings, and we can work with data real time through this system. So this is enabling our data integration and real-time data access, both read and write between the services we want to use and the facility itself. So this is what enables the digital twin interconnectivity in our systems. So why did we need this? Well, we want to do a lot with the data we collect, but the issue is who provides the data? Well, the equipment is running, we collect data, but do that data have a context so we can actually use that for anything? It didn't in our old strategy. So it's really about, if we want to do research on data-rich systems, we need high quality data and we need lots of it. We want a way to store the data, which is easy, and we want a way to store the context of the data. And that is basically the one of the motivation between how we set up this infrastructure and the SCADA project in itself. So I have a brief video here that I'm just seeing if I can run. Oops. I should be able to, maybe if I take this out. Yes, I can run it here. So here you actually see the SCADA interface of our systems. So there's a number of unit operations. You have this operation tab here, which gives you the most important I/O signals in a dashboard sense. You have also the P&D diagram in this with the live sensor readings, where you also have the opportunity to give commands directly to the system that then change the operation of the process. We have also for how to operate that as a PDF file within this same framework. And when you're actually executing the system, then you record data when you start operating. So the Siemens system will take data 24/7, but we will enable when we actually have to save data and when not to save data. And we have a page where you can put in, for instance, all the metadata. So if you take a physical sample that you run in a lab analyzed by titration or something else, you can put the results in so it's stored with the right data tag, and it keeps all the relevant information in one package together. So that is how we have built up this system. So basically, we want also to use this to a more advanced setting. So yes, we have sensors, we have feedback system, we have model-based control, as Antonius also discussed. This is known as what is we have in also the industry 3.0. But when it comes to the advanced operation, when we are having IoT-enabled sensors, when we have large parameter models running machine learning in real time running on our systems, and when we have big data interconnected systems, how do we actually deploy these systems? And we want to look into those kind of complexities as well. So we have considered different kinds of deployment. So one thing is, of course, a deployment directly between one piece of one computer to one physical systems. But with this enabled system, we have the ability to actually read and write real-time data through this cloud solution to a PC, where we can then run custom code and deploy whatever things we are testing out for validation in this system. So this is actually what gives us the opportunity in terms of development of Digital 12. Of course, here we will then be restricted by the PC that is then running the application. So ideally, we are moving more to the set where we actually both have the data interconnection in the cloud, but we might also running our, for instance, machine learning models or our scheduling operation or our real-time control computation in the cloud on the server as well, while we are more having a dashboard surveillance to the system. So we are looking, how do we actually, for different kind of engineering problems, how do we develop and deploy in an efficient way these to the physical systems? So we have some case studies we use to investigate these. We have a fermentation setup where we collaborate with the University of North Carolina, BTech system to do a virtual laboratory based on one of their setups they use a lot for furthering education. We have a bubble column in-house here in the department where we are looking into hybrid modeling, so how to model both with mechanistic insights and machine learning to get information out of such a process system. And we have a batch distillation system where we are trying to use a digital shadow setup in order to create interfaces that whoever is operating this system can get a simulation information of this system, not just a sensor reading, but actually understanding what is going on in that system. So this is part of our development in this, which is now enabled by this infrastructure. So if we look at the batch column here, as you can see on this simplified PI diagram, well, we have both analog and digital sensors. Basically, you get some temperature information about what is the performance of this system. It's a batch system, so it's unsteady operation. You have several manual inputs, and it's an exercise running frequently in our lab. So basically what we would like to do here is to build a digital shadow. We have the real-time data interconnection. We have a simulation model of this system. So we would like to be able to show, for instance, concentration profile or other key information in real time to the students while they're operating this system on a separate interface in order to give an idea about what does these numbers mean. That could hopefully lead to better process interventions when they are operating the system. So this is the kind of examples we're trying to investigate. I have a little bit in this case for the bubble column. It is a fairly sizable equipment. We are investigating mass transfer of oxygen, hydrogen peroxide catalytic methods. So we make a supersaturated solution, and then we see how the dissolved oxygen profile is then coming down to the saturation level when you are bubbling gas through this system. It is on our SCADA platform, so we have this real-time data connection to this system. And basically what we're investigating here is hybrid modeling. So we have a lot of data series from students who've just been running experiments. They are, through those experiments, changing operating conditions on liquid flow rate and airflow rate in this two-fluid nozzle, which is implemented on the system. So we have a number of data series that we can use for training our models. And as you can see here, even though all students are running the same manual, there is a significant variation between different operations. So it actually mimics very much how industrial data looks, even though you always try to keep your system in steady state. So for this particular system, we modeled the dissolved oxygen in the system. So we have a contribution from adding hydrogen peroxide to the system. We have a contribution for the mass transfer from the liquid to the gas. We have a balance for the hydrogen peroxide, and we have a measurement equation acknowledging that we might both have noise and bias on the sensors inside the system. And with this simple model framework and this mechanistic understanding, basically we are trying to estimate these unknown parameters relating to the reaction rate and the mass transfer coefficient. And instead of using a correlation, we do this based on machine learning. So we make a model like this where we basically train a neural network in order to predict what is the KLA in the system based on different operating conditions, and we then deploy the model like this as a hybrid model. So we have, for instance, used this system to be able to make a comparative study about different ways of doing this hybrid AI modeling. In this case, we worked together with Professor Venkat from British Columbia University, benchmarking a similar parametric hybrid modeling approach with a symbolic AI. Not to advocate any system, but simply just to make a fair comparison about different ways of solving a specific problems, discussing pros and cons. And I think this is a great example about how there's a need for some examples about showing this is how it can be done, and this is the properties of different modeling approaches, and this is these are the difficulties related to employing such models. So this was all based on training on historical data sets. In reality, we would like to go on and do this as an online application. So we train the machine learning model while the equipment is actually running. And in order to do that, we have the real-time forecasting is right now happening on a local PC. We have tailored the machine learning model so they're actually fast enough for retraining with the sampling rate that the data come in. And right now we are working on deploying this model on Docker. I would hoped I could have shown you results, but my students are working right now in the lab, actually trying to show that all these elements come together and we can have machine learning working in real time, doing model retraining, looking what happens when we go outside the training region or other instance for this kind of system. It's a very nice system where we can get some insights into how easy or difficult it is to deploy these opportunities in a process systems. So that was one leg. The other leg we have been investigated is related, but it's not exactly the same. This is applying virtual reality as a training platform for our students. So the issue is we have a lot of bachelor students coming in, typically running a course on experimental unit operation. They have to run a different number of exercises and write reports for this over an intensive period of typically 3 weeks. The learning objectives is then to be able to understand and describe the function of industry-like equipment, be able to operate this and secure data from the measurement systems and the data analysis needed, for instance, lab analysis, and then evaluate and make conclusion based on their experiments. So a classic unit operation lab. Our challenge is, however, that they prepare on written manuals. They go and perform an experiment, for instance, like this ion exchange system, and when they then do the reporting and reflect about how well their observations fit with the theoretical developments, they do have issues about when they actually understand the system well enough. That typically happens in the reporting phase, and sometimes it's difficult for them simply to go and perform the experiment just based on the written manual. They don't prepare well enough for a number of reasons. So they feel ill-prepared, and often we experience that they need quite a lot of support, both based on the safety, how to use utility system, how to interconnect with the HDMIs and so on, how to operate a system and getting it into stable operation so that they can get valuable data. So that was the background for issuing some of these digitalization initiative also. So we combine now exercise manual with a virtual reality platform where they actually get a completely different understanding about how the system, the physical system appearance looks and how the operation of the system goes. So the information in the manual and these virtual reality instruction videos are in principle the same, but it has a completely different visual communication that enhances their understanding and makes them more independent. Also, we have streamlined the HDMIs with this new SCADA interface, and that also means that they're much more familiar about how they operate different systems once they've tried one of them. So that is also helping out how they execute the experiments in our labs. So we have many equipments we use for these courses. A number of them are integrated on the SCADA system. These are usually the more complex type equipment, which is more instrumented. And a number is also related to these virtual reality videos. And this is also typically the more complex systems where it is harder to understand just from reading a manual how the PI diagram reflects to the physical systems. So on. But we are developing this and is expanding on it as we go along. So this virtual reality platform that we develop, we have that for a crystallizer system, an absorption column, the bubble column, and the batch distillation column. We have it for the falling film evaporator, an ion exchange column, and an exercise for cleaning in place. And just to show a little bit more in detail, I actually have also a video for this, so you can see. Now you are actually seeing what you would see if you were looking at this either through 3D goggles or on your own tablet. So we have 3D modeled our entire process hall, and that allows that the system, people can actually understand this 360 dimension of a physical equipment. The manual is broken down in a number of steps, so they can go into see, for instance, in operation, how to execute a certain step. And as you can see here,
open the main steam valve by turning it counterclockwise as far as possible. Then turn it half a rotation clockwise. Open the valve, V40, and use the pressure reduction valve, V41, to adjust the pressure displayed on PI6. Adjust the valve until a pressure between 0.5 and 1.0 bar P is achieved.
So this simple video demonstrates very neatly how the student would use this in complement to a written manual to understand where is it that a certain valve or sensor is located, and when I have to open it, it actually means I have to take them from this position and move it over here. It makes them much more confident and independent of our support when they're running experiments. So what is the impact of this? Well, I must admit, we only have qualitative results so far. We have tried to get a lot of feedback through questionnaires. We are expanding these surveys, but it is not easy to get the high answer percent from students who is busy running exercises and a running report. But hopefully we at some point will get some data that actually allows us to come to some solid conclusion how this actually impacts their learning process. What we do see is we have a high student appreciation. They find it fun, they think it's relevant, it's useful for both in preparation, but also in the operation of this system. They also get faster starting and they execute lab tests and other small things much faster and in more control and with less need for our support. Does it improve the learning outcome? Well, yes, they understand the parts and the principles of the system. They understand the operating of the system, but how this platform so far have been constructed, we basically made a visual representation of the operational platform, not the scientific content. So right now, it's difficult for us actually to see, did it prepare them even better for writing better reports? Did they get also an understanding of the underlying phenomena, which is the purpose of the exercise? And this is something we are looking into to see, have we designed the system correctly? And is this a bonus that we sort of relieve some energy for some parts, that they get more energy to sort of absorb the engineering content of these exercises. Good. So what is our next step? We have gone as far as you have seen now. We plan to expand to more units. Basically, we would like to have our SCADA system covering a full biomanufacturing production line. So all the steps from fermentation into purification, also to be able to work with the data in research related to biomanufacturing. We want to use this infrastructure to see how you actually deploy and develop sensible digital twin frameworks, which is practical, and see how we then bring value out of it, whether it is a digital shadow doing visualization for operator support. Can we bridge this information from different unit operation to support planning, scheduling type questions? And also, as you have seen, we are working in deploying hybrid modeling with physics and AI type information in the framework. And then, of course, we investigate, does this actually make an impact in engineering education? We need a better data foundation in order to make solid conclusions, but at some point we will pursue publications in relation to this as well. And we will very much like to use our facilities to build consortia, both with research institutions and industrial collaborations, because we believe we have some facilities which is fairly unique. So based on that, I will thank you much for your attention, and I'll be happy to answer questions.